Imagine waking to the news, a black hole is heading towards Earth. The shock would give way to one pressing question: can it destroy us? The answer lies in astrophysics' most mind-blowing aspects. Black holes are regions where gravity is so strong, not even light escapes, formed from massive star collapses. But for Earth to be at risk, the conditions must be just right. Consider a stellar mass black hole, about 10 solar masses, approaching Earth. The Roche limit, where tidal forces overcome Earth's cohesion, would be just a few hundred kilometers away. At this proximity, gravitational effects would distort and break our planet apart long before accretion. Yet, detection at such a distance is virtually guaranteed with current surveillance, making a stealth approach impossible. The gravitational waves emitted during its approach would also alert us years in advance, a cosmic early warning system. Speculatively, Hawking radiation could play a role, but its impact on Earth would be negligible unless the black hole is incredibly small and close. More intriguing is the opportunity a nearby black hole would present: unparalleled scientific discovery. Observing its effects on spacetime, testing general relativity in extreme conditions, and potentially unlocking secrets of quantum gravity. The data collected could redefine our understanding of the universe, making the black hole a cosmic laboratory. The likelihood of such an event in our lifetime? Extremely low. The closest known black hole, Gaia BH1, is 1,560 light-years away. At cosmic speeds, fast is still millennia to reach us. Thus, while a black hole destroying Earth is theoretically possible, the universe's vastness and our growing vigilance make it a distant, albeit fascinating, concern. Instead, black holes serve as a reminder of the awe-inspiring scale and mystery of the cosmos, driving human curiosity and the pursuit of knowledge. As we ponder the black hole's approach, consider the cosmic ballet of gravitational influences. Even at vast distances, a black hole's gravity would perturb Earth's orbit, causing minuscule but measurable deviations in our planet's path around the Sun. This gravitational tug would be imperceptible to us but detectable by the most sensitive astronomical instruments, serving as an early warning system. The challenge lies in distinguishing this signal from the myriad other gravitational pulls in our celestial neighborhood. Delve into the heart of accretion, the process by which a black hole devours its surroundings. As Earth approaches the Roche limit of a 10 solar mass black hole, approximately 400 kilometers away, tidal forces would stretch our planet into an ellipsoid, eventually breaking it apart into a trail of debris. This spaghettification occurs because the gravitational pull on the near side of Earth would be significantly stronger than on the far side, a differential force that no known material could withstand. The debris would then spiral into the black hole, emitting intense X-rays as it heats up, a final, fleeting signal of our planet's demise. Speculate on the role of Hawking radiation, a theoretical quantum effect where black holes emit radiation due to virtual particles near the event horizon. For a stellar mass black hole, this radiation would be minuscule, posing no direct threat to Earth. However, if we were to hypothetically encounter a micro black hole with a mass similar to a mountain, about 10 to the power of 15 tons, Hawking radiation could become significant. Such a black hole would evaporate rapidly, emitting a burst of energy equivalent to thousands of nuclear bombs in its final moments. The challenge in this scenario isn't the radiation itself but detecting such a small, elusive black hole before its explosive demise. Reflect on the broader implications of a close black hole encounter for our understanding of the universe. The observation of such an event would be a once-in-a-human history opportunity, akin to having a cosmic laboratory at our doorstep. Scientists could gather unprecedented data on black hole physics, from the behavior of matter in extreme gravitational fields to potential deviations from general relativity. Moreover, the very presence of a black hole near Earth would force a re-evaluation of our solar system's dynamics and the long-term stability of planetary orbits, raising fundamental questions about the resilience of life in the face of cosmic uncertainties. As the hypothetical black hole recedes into the vast expanse of space, we're left with more questions than answers. The interplay between black hole physics and planetary survival serves as a stark reminder of our place within the cosmos. Though the likelihood of such an encounter is low, the intellectual pursuit of understanding these phenomena drives human innovation and our relentless quest to map the unknown. Envision a stellar mass black hole, about 10 solar masses, approaching Earth. At a distance of roughly 100 astronomical units, AU, the black hole's gravitational influence would start to perturb Earth's orbit subtly, causing minute fluctuations in our planet's axial tilt. This, in turn, could lead to extreme and unpredictable climate shifts due to altered seasonal patterns. The black hole's presence would also distort the Oort cloud, potentially sending comets towards the inner solar system, posing an additional, indirect threat to Earth. As the black hole draws closer, within about 10 AU, its gravitational pull would become strong enough to affect Earth's tides, amplifying them to catastrophic levels, far exceeding the highest tsunami waves. The Moon, now in a destabilized orbit, might even collide with Earth or escape into space, depending on the black hole's exact trajectory and speed. Delve into the accretion process, where the black hole's gravity overwhelms Earth's. At the Roche limit, about 200 kilometers for a 10 solar mass black hole, Earth would be torn apart, with the black hole consuming our planet's matter. This process would not be a clean ingestion, instead, it would create a violent accretion disk around the black hole, emitting intense X-rays and gamma rays, potentially sterilizing the surrounding space of any life forms before Earth's complete accretion. The energy released would briefly outshine the entire galaxy, a cataclysmic signal of our planet's demise. Consider the speculative role of Hawking radiation in this scenario. While negligible for large black holes, for a small, stellar mass black hole, Hawking radiation could theoretically contribute to the black hole's evaporation over billions of years. However, this timescale is vastly longer than the time it would take for the black hole to either miss Earth entirely or collide and destroy our planet. Interestingly, if the black hole were small enough, on the order of a few solar masses, and passed close enough to Earth without accreting us, the transient increase in local Hawking radiation could, in theory, be detected by future, highly sensitive instruments as a brief, unexplained energy spike. As we contemplate these cataclysmic scenarios, remember the vastness of space and the improbability of such an event. The closest known black hole, Gaia BH1, is over 1,500 light-years away, a distance that underscores the statistical safety of our cosmic neighborhood. The true aha moment comes from realizing that the study of black holes, even in hypothetical Earth-threatening scenarios, drives innovation in astrophysics and cosmology. Technologies developed to detect and study black holes, such as advanced telescopes and gravitational wave detectors, have broader implications for understanding the universe. For instance, the development of more sensitive gravitational wave detectors could reveal more about the universe's violent events and possibly even the formation of black holes themselves. Moreover, the computational models created to simulate black hole interactions with planets could enhance our capabilities in predicting and mitigating real, more probable cosmic threats, such as large asteroid impacts, by improving our simulation technologies for complex gravitational interactions. Envision a futuristic laboratory, where AI-generated visuals of black hole simulations dance across screens. Researchers, surrounded by sleek, silver equipment, observe as a stellar mass black hole, about 10 solar masses, warp spacetime in the virtual realm. The AI, processing terabytes of astrophysical data, generates a mesmerizing, swirling accretion disk, complete with vibrant, neon-like emissions. This isn't just art, it's science. The simulation predicts the black hole's behavior, crucial for understanding potential Earth encounters. For instance, if such a black hole were to approach within 100 astronomical units, about 9.4 billion kilometers, its gravitational influence would start to perturb Earth's orbit, leading to catastrophic climate fluctuations. The room falls silent as the AI projects a what-if scenario, Earth at the Roche limit, its oceans bulging like liquid in a cosmic centrifuge. The implications are clear. Even a small black hole's proximity would be cataclysmic. Yet, the probability of such an event, given current astronomical surveillance, is near zero, a comforting thought amidst the awe-inspiring simulation. Delve into the heart of computational astrophysics, where algorithms weave complex narratives of celestial mechanics. Consider a supermassive black hole, millions of solar masses, at the galaxy's core. The AI generates a breathtaking, cosmic dance, stars orbiting, their light bending around the void. But zoom in on a smaller, stellar mass black hole, and the AI illustrates a critical point: the tidal disruption of a planet. Imagine Jupiter, its gaseous body stretched into a long, glowing stream as it crosses the Roche limit. This simulation isn't just about destruction, it's about understanding the delicate balance of gravitational forces in our universe. For example, if a black hole were to pass close to our solar system, the outer planet's orbits could become chaotic, potentially ejecting Earth into interstellar space. The AI's visual feast ends with a stark message: the universe's beauty is intertwined with its capacity for destruction, a duality that fascinates and humbles us. As we ponder the intersection of black holes and our planet's fate, a solemn, deep space backdrop unfolds, with Earth a fragile, blue dot against the inky vastness, a reminder of our place in the cosmos. Picture an AI-driven observatory, where telescopes and satellites feed real-time data into a supercomputer. The mission: to detect the impossible: a black hole on a collision course with Earth. The AI processes decades of astronomical data, searching for the slightest perturbations in star motions that could indicate an unseen mass. Suddenly, an anomaly emerges, not from space, but from the depths of the AI's predictive analytics. A hypothetical scenario unfolds on the main screen: a small black hole, undetectable by current means, approaching from the direction of the constellation Orion. The AI calculates the time to impact: centuries, not years, a relief, yet the exercise exposes a glaring truth. Our detection capabilities, though advanced, are limited. The universe holds secrets, and sometimes, the most dangerous threats might be those we're not looking for, hidden in the vast, unexplored expanse of space. For instance, a black hole of 10 solar masses passing through the Oort cloud could disrupt long-period comets, potentially sending one towards Earth, a secondary, unforeseen hazard. Imagine standing at the edge of a futuristic, underground research facility, where the world's leading astrophysicists gather to simulate the unsimulable. Their focus: the ethical implications of discovering a black hole inevitably bound for Earth. The AI, now a facilitator for global strategy, projects scenarios on a massive, curved screen. From coordinated evacuations of affected regions to the more controversial topic of attempting to nudge the black hole's path using futuristic, high-energy propulsion systems, no option is left unexplored. The simulation ends, leaving behind not just strategies, but a profound question: in the face of cosmic inevitability, what does it mean to be human? The answer, much like the black hole itself, remains a void, waiting to be filled by the collective ingenuity of humanity. This existential challenge could unite the world in a shared purpose, transcending borders and conflicts, as we confront the ultimate test of our species' resilience and cooperation. Envision an AI-generated visual of a futuristic, spherical observatory, floating in the depths of space, with a massive, high-resolution screen wrapping around its exterior. This screen displays a real-time, data-driven simulation of a black hole's accretion disk, with vibrant, swirling clouds of gas and dust, illuminated by intense, pulsing X-rays. The simulation zooms in on the black hole's ergosphere, where the curvature of spacetime is so extreme that it warps the fabric of space around it, dragging nearby matter along with it. This is where the black hole's rotational energy is extracted, a phenomenon predicted by the theories of Roger Penrose and Kip Thorne. As the simulation unfolds, the screen highlights how the ergosphere's boundary, the static limit, dictates the region where the black hole's gravity dominates, inevitably pulling in any nearby object, including planets like Earth, should they venture too close. The implications are profound. The point of no return, the Roche limit, varies greatly with the black hole's mass, a stellar mass black hole requiring an improbably close approach to affect our planet. Yet, understanding these dynamics through AI-driven visualizations revolutionizes our grasp of astrophysical catastrophes, making the unimaginable, tangible. As we delve deeper into the mysteries of black holes, the cosmos reminds us of its awe-inspiring scale. Pexel's video, Galactic Expanse Starfield with Distant Supernova.